So what do you see?
Well, there's two steps, I guess.
Cool. Which step do you care about?
The one that's going to A.
Cool. Why are you ignoring the step to B?
Because you have to have A first.
Good. Okay, so we don't care about B. All we care about is A. So now what do you see? Right? Because that could seem like I was just talking with Caden. Let's open it up to everybody. This is to everybody. What do you see?
There's pi bonds.
True. We've got pi bonds in there. We see bromine as a potential leaving group, which is really a fancy way of saying we say a partial negative and a partial positive. Let's just start with those two. Which is more likely? Should I be looking at the pi bonds or should I be looking at the bromine as a leaving group? Why? Why is the pi stable in the ring?
Resonance.
So while we may be looking at the addition chapter, the aromatic ring is not something you should be touching. So if you're seeing a 6-membered ring with 3 pi bonds, yes, those are pi bonds, but those pi bonds are very, very stable pi bonds due to the conjugation and the resonance within that ring, which means our primary focus should be out to that bromine. We've got a partial positive on our carbon. We've got a partial negative on the bromine. Right? What reactions have leaving groups?
Like elimination reactions? Or?
Elimination reactions have leaving groups. What other types of reactions?
Substitution.
Substitution. Okay, so in this particular case, you would need to be deciding which path do I need to take. Should I be taking substitution or elimination? Well, what's the differentiation between substitution and elimination?
A good leaving group versus not?
Nope. A leaving group is consistent for all of them.
Like a nucleophile?
Nucleophile or base. The nucleophile is something that we would see in a substitution reaction. Base is something we'd see in the elimination reaction. Those are the fundamental characteristic differences between them. How do we decide which one we have? Okay. So the first argument that I would kind of push out here is you all did a great job looking at the very first thing you saw. Okay. And identifying that is okay. But I would argue you should have first and foremost looked here. What's within that red circle? So for the recording's sake, I heard, I don't know what it is.
What it's reacting with.
It is what it's reacting with. Why else should you have looked there? It is going to tell me how the reaction works, but first I have to understand something about it. And what we've already heard is that I don't know what it is. Okay? When we looked at the blue thing, you looked at the blue thing because why?
It's already there.
The red thing was already there too. Why'd you look at the blue thing first? Simpler? You're going to argue the blue thing that takes up this giant box is simpler than that tiny little red circle?
Yes.
It's a bit of a stretch. What's that?
Just go left to right. It's like reading a book.
Reading a book. It's the very first thing you encounter. Okay? This is something that you have to be aware of. When writing a multiple choice test, we have to ensure that you're getting the answer right because you understand it, not that you lucked into it. So the very first simplification that we can do as exam writers is to ensure that it does not match left to right. Because if it matches left to right, you're lucking into it based off of your reading skills. We're not testing your reading skills, we're testing your chemistry skills. So instead of reading left to right, recognize that we're trying to understand the chemistry And we should be looking for chemical reactive things. So by looking at that first structure and saying pi bonds, I'm okay with that. Pi bonds are potentially reactive. Seeing the bromine, potentially chemically reactive. All of that is good within that piece, but you still need to break through that first barrier. It's not just reading left to right. It's look for the most reactive thing. Okay? Pi bonds are high in reactivity. Why did no one reference the carbon hydrogens or the carbon-carbon sigma bonds? Nobody said this carbon to that carbon bond. Nobody talked about those hydrogens. Why does it make no sense? Why is it not reactive?
It's even, nice even pull on each.
Nice even pull on each because
Electronegativity.
equal electronegativities. So when we're trying to find the reactivity, our first pass through, yes, may still be left to right. Okay, and we just discussed in exam writing that maybe reading left to right is probably a bad idea because exam writers are trying to nullify that reading effect. Maybe we should try reading right to left. Okay? Ultimately, there's a small time difference, so it's not a big deal. Okay? But I would argue again, still, we should have seen that red structure. We didn't talk about the carbon to hydrogen because those were equal electronegativities. Those are non-polar covalent bonds. What bonds should I be looking for? Polar covalent's a good intermediate first step. Ionic. How do I know I have an ionic bond? I don't know what T-bu means, Mike. Okay. Do you know what K means? Is potassium a metal? What's that potassium bonded to? An oxygen. I don't care what T-bu means theoretically at this point. Okay? What I care about is that I have potassium as a metal and O-T-bu as my negative. The metal can drop off, and what I'm looking at is that now negative oxygen. Okay? Do I need to know what the T-bu means? Yes. Okay? So we are going to run into a wall there. There's always content that you have to know something about to a certain extent. Why do you not know what T-bu means? Why did I not make you learn it?
Figure it out later, kind of repetition.
What did I say was the most important thing for you to be learning? The chemistry. What is T-bu?
The molecule.
I think you mumbled it. Nomenclature. It's the name of the thing, not the chemistry. Okay? So it is okay for you to be like, I don't know what it is. What should you immediately do then? Ask. What if it shows up on the exam?
Work it out. Notice K.
Ask. Okay? The exam does have some information for abbreviations like this, but these are abbreviations, they're code words. Okay? Theoretically, if you're going to become an organic chemist, you would need to know what those code words mean, but the most important part is understanding the structure and the chemistry behind it. So what does T-bu mean? What do you think the bu stands for? That's a stretch. Never mind. I'm going to ignore that question.
U.
Maybe you actually said it. What did bu? Bu for butyl. It's an abbreviation for the butyl group, meaning 4 carbons. Do you see 4 carbons now? Yeah, there should be 1, 2, 3, 4 carbons. Okay? Do you have a butyl?
Yes.
How do we do nomenclature? Because nomenclature is part of the exam. Abbreviations float in a weird gray space.
Find the 3 chain or longest carbon chain.
The longest carbon chain. What's the longest carbon chain?
3.
3. Is that butyl? No. So do you have butyl? Why the heck do they call it butyl? What does the T stand for? It's not tetra. It's tert. Tert for tertiary. What this is saying is that we have 4 carbons arranged such that I have a tertiary spot. Where is there a tertiary carbon? The number 2 carbon. The number 2 is a tertiary carbon. That's where my oxygen is connected. So by writing OT-bute, we're specifying where the oxygen is connected. It's connected at the tertiary carbon. If we connect it anywhere else, it's no longer T-butyl. Okay? This has an extra salt to the wound, in my opinion. This isn't IUPAC nomenclature. This is a common name. We were building small structures initially, and we had to come up with some naming system. So we just started calling things Bob. Okay? OT-bute is a Bob name. Okay? There's some logic behind it, but it's not a logic that holds consistent for larger molecules. Which means IUPAC came through and said we shouldn't use this name anymore. Why do we still use it?
It's easier.
A repetition, we've already used it, everyone knows it.
There's so many old people that have used it for so long, and what do old people do when it comes to change?
Complain.
They don't, okay? Or they complain about it to prevent said change. Okay, that's not a blanket statement. Okay, not all old people do that, but that's generally speaking what happens. Okay, and sometimes it's just in our abilities. The older we get, the less we care about things. No, I'm not going to change. Screw you. Okay. Dad was a huge example of that. Okay, so on an exam, if you see that, you can ask. Okay, I might tell you it's on the front of the exam so that I don't have to draw it out. Okay, so check. Okay, but you don't have to check, you can ask me first. Okay, same thing for THF. I think that's also one that's included on the front of the exam. Okay, why are you not concerned about THF? Where are you?
Salt,
It's the solvent. It's tetrahydrofuran. Okay, how do you know it's the solvent?
the bottom.
It's written underneath the arrow. Again, not a perfect scenario, but that's generally a first baseline pass. Okay, so there's our THF. So if we now go back and look at this, we've established that we've got this nice partial positive, a partial negative on the bromine. Which of those is more important to the chemistry of the molecule? It's kind of a hard question. So partial negative. So I would expect the bromine to act as a nucleophile or a base. Should that bromine donate its electrons? Say again?
No,
No, why not?
because it's gonna take electrons so it can leave.
So if we're looking at that bromine, it has 3 lone pair electrons. Yes, it is partially negative. Would I expect those electrons to donate out to an H+? Would I expect that result? No. Okay, why not? Bromine doesn't want 2 bonds. Remember those common bonding patterns we talked about at the beginning of the semester that you should memorize? There, you've got an immediate fallback to. You told me it doesn't do 2 bonds. Okay. Okay. Why should it not do 2 bonds? Then it's charged. Is bromine an element that would like to be charged? Okay, so you've got lots of explanations for why bromine should not donate its electrons. And if bromine doesn't donate its electrons, is the partial negative the one that's reactive? No, it's the partial positive. Okay? Understand how we process those pieces. Okay? We're always falling back to the definitions of what those things can act as. How could I stabilize that partial positive? I like that explanation better. So one argument is to take electrons from a hydrogen. We take a hydrogen, take those electrons nearby, and we shuttle them over. Okay? That would create a pi bond indeed, and we could kick out the bromine. How else could you stabilize that positive?
Make the oxygen and just break that off.
Say it again. I think you said it.
Connect the oxygen and then have a molecule break off.
You're taking that negative oxygen, so the oxygen's acting as
And the oxygen, the nucleophile.
a nucleophile. How do we break off that hydrogen? What did the oxygen act as? It acted as a base to remove that hydrogen. So if it acts as a base, we get elimination. If it acts as a nucleophile, we get substitution. This is why this reaction becomes challenging. Depending on our source of electrons, whether we're nucleophile or base, it changes the outcome, which is why we have to be able to look at that reagent and say, what is it most likely to act as? How do we make that differentiation? It's based off of the structure, which is why you need to know that abbreviation T-but equals the thing up there. Right? So now that we have the thing up there and our two possible outcomes, what do we think that structure should act as? Should it act as a nucleophile or a base? Why should it act as a base? Okay? The difference ultimately between bases and nucleophiles is how they react. Bases react on the surface of the molecule. They're reacting with hydrogens. Hydrogens on the outside of a molecule. Nucleophiles react with things inside the molecule. You have to get past the hydrogens. So if your source of electrons is very large, it can't get past the hydrogens. So it can't react as a nucleophile. Large molecules tend to act as bases. This is the stereotypical base that is used when we want to do an elimination, is T-butoxide. Okay? This is our base. And since we now know that it's acting as a base, we can say that base comes in, removes the hydrogen, and the end result for that structure, for structure A, let's not do any bond rotations. We then put the double bond out there. Floating around, we'd also get bromide floating around. Okay, so this question makes you push back to content that you've already addressed. Okay, this was the past unit. Okay, this becomes more challenging when you're trying to process it because it's sitting in the addition chapter. And what do you assume you should be doing in the addition chapter? You should be doing additions. So our primary focus shifts to the pi bond. We have to be real careful of that, particularly as we advance through OChem. Initially, that's not a bad assumption because you don't know any other chemistry. You now know a significant amount of chemistry. You have to be really careful just saying, oh, it's in the addition chapter, so I want to do addition. It may not be the case. Make sense? That sets us up with structure A. So now what happens? Now we have to move to the next reaction. It reacts with HBr. What should we do now? How do we decide to run our reaction?
To the left or the right? I mean, no.
So the question that should be asked is,
It's most reactive.
what do you see? What's the most reactive thing there?
An alkene and a brom pulling negative, making hydrogen positive.
Okay. So when I ask for the tallest person in the room, you list 5 people. Does that make sense?
Yeah. No.
Why does that not make sense? Tallest means 1. Okay? So not that you're wrong, but process what you're being asked to look for. And if you start coming up with a laundry list of things, that means you're going to get a laundry list of possible outputs. Okay? So what's the most reactive thing? Okay? 2 answers should come out, and you did list both those answers, okay, for the record. Okay? We have HBr and we have the alkene. That's not most. That's 2 things. Most. You're right.
HBr because it is a strong acid.
HBr because it's a strong acid. Remember how I said there's things that you should have been taught to memorize way back when? We've gone over it again and again and again, both within this semester, and HBr has been one of the highlights. Okay, HBr is a strong acid. Okay, so if we think through what's the most reactive, like I'm doused with alkene. Is it a dangerous alkene? Like, maybe. I'm doused with HBr. Oh crap! Get me in a shower. There's this huge reactivity difference there. Use that to your advantage. You know HBr is an acid. Okay, I don't want an acid on me. Okay, because it's an acid, how does it react?
Very active.
Breaking the pi bond. What if there's no pi bond? It's still an acid. How does an acid react?
Proton die?
The acid reacts because the electrons in the bond between the hydrogen and the bromine go to the bromine, which is generating a very large partial positive on our hydrogen. Yes, we're forming an equally very large negative on the bromide. Bromide. Why do I not care about it?
It's really good at handling the charge.
For the same reason I didn't care about it back here. Okay? It's effectively a leaving group. It's stable on its own. It's not reacting. Okay? I need to get rid of the H first. So I have a large H plus. What do I need to stabilize a large H plus? Electrons. Where do I have electrons? Now I've got the pi bond to fall on. So I can have the pi bond share electrons with that hydrogen. Bless you. Just realized I rotated the pi bonds, but hopefully that won't matter. So I have to place the hydrogen. Where do I place the hydrogen? Call it red or green.
On the green. Wait, hold on, yeah, green.
Okay?
Red.
Tough.
Carbocation.
Okay.
Green.
Which becomes the next issue. Our focus is on the atoms, but we rarely realize the secondary piece. The secondary piece is once we put the hydrogen on there, we have a carbocation that necessarily appears. The electrons in our alkene were shared between two carbons. If I take those electrons out to share them with the hydrogen, the other carbon lost its electrons. So if we place the hydrogen at the green, we're placing at the red a carbocation. Is that a stable carbocation? No, because that's primary. So where should we place our hydrogen? At the end, so that I can, get my carbocation forming there. So far, so good? Okay. Cool. What else formed? Br minus. Now that I have Br minus, bromide, I now have an active nucleophile. It's negatively charged. We want to neutralize that charge. It could act as a nucleophile and react back with that positive charge, okay, in a coordination reaction or a coordination mechanistic step. Okay? That would complete to an answer which I'm going to guess, Caden, is the one you drew. Sorry, I just brought you back in the middle of that. Did you draw that and get it wrong? Yeah, okay, cool. Okay, well, not cool that you got it wrong, but okay. Cool, that makes sense. That's good logical flow behind that. The piece that we now have to be aware of. When I say SN1, you're supposed to say carbocation. And when I say carbocation, you're supposed to say, do we have a carbocation? I don't care that I didn't do SN1, but carbocations necessarily need to be considering rearrangement and resonance. Both those R words need to appear. Okay? I've got a secondary carbocation. That's not the greatest. That's the bottom tier. It's allowed to form, but it's the bottom of my list. Could I rearrange? Could I shift the red hydrogen over? Well, that just puts the carbocation in the primary position, which we didn't like, right?
Yeah.
Which then means where should we look? The other side. There's technically two hydrogens there. Could I rearrange one of those? Right? Yes, I could. Yes, we could with the red one, but we decided not to draw that, right? The furrowed brow is exactly what I was looking for, Caden. So it sounds like you've already processed out what that looks like in your head, which is good. Putting the carbocation in there. We don't need to worry about the hydrogen, the red hydrogen anymore. Okay with that? Do I need to show the blue hydrogen at the green position? Are you okay with that? Okay. So furrowed brow, why was the furrowed brow?
Because it didn't change, it's still secondary.
This is a secondary green carbocation. This blue carbon is also connected out to two carbons, so therefore it's secondary. And if it's secondary to secondary, it should not rearrange. okay, because there's no driving force for it. Is it technically secondary? No, why not?
Ions from the ring are resonating with it.
That, it's not even a tertiary, don't push that far. We have resonance stabilization. So it's not secondary, it's secondary plus to our notation. So it went from bottom of the ladder to like 3 or 4 steps up. Okay, so that is a significant stabilization. Should we be looking at all of those resonance structures? Yeah, we should. We should technically continue to draw the resonance where we're pushing the carbocation all the way around the ring. Okay? And then we'll note that it comes right back out to the blue spot. Okay? Are those important? Yeah, let's just run with it. Are those important resonance structures? Okay. So some people are saying no, which is the answer I'd go with, so I'll play the devil's advocate, and I'd say yes, they're important because it allows us to know that the rearrangement happens. Okay? So that's why it is important. Why is it not important? Charlotte, what do you got for me? Yeah. So if I'm going to look at the continuing reactivity, should I be reacting the purple structure or the blue structure? Okay. That is when we say, are those resonance structures important? That's really what I'm getting at. Do I need to be looking at the result of those resonance to say my chemical reaction is going to continue from the purple or does it continue from the blue? So people saying no, what I feel you're telling me is the purple structures it does not continue from, it continues from the blue, which is good. Why does it continue from the blue and not from the purple?
Carbocation go in either direction.
It can go in all of those, and there's 2 more resonance structures that are not drawn. Yeah. Why is my focus only on the blue?
Resonance of the ring.
Those pi electrons from the ring are uber stabilizing, okay, of each other and of the carbocation. Which do they prefer? Of each other. Okay, which is why the resonance is important, just to show that my blue structure is better than my green carbocation. But that blue structure is where I'm now going to continue my reaction from, because the purple ones are too reactive, too unstable. Okay? And if I'm going to continue that reaction, I need something to stabilize that positive. What do I have to stabilize that positive? I'm going to have to erase that structure. Does that make sense? Okay. Because I can't see what the rest of the question asks. There could be another wrinkle to this. Okay? Could be. I think you're actually okay with this one. Yeah. Okay. But what could be the other wrinkle to this?
Would be if it's wedged or dashed.
Where that bromine is connected is now a chiral atom, which means, should I be concerned about stereochemistries? Should this be a wedged bromine or a dashed bromine? It's both. Why is it both?
I just know it's both.
Where the bromide formed the bond reacted with the carbocation. The carbocation is located on a p orbital, which is both above and below the plane of the molecule, which means the bromide could come in and be wedged or dashed. Technically, we'd have to show both. Is this a big issue for you as far as the smart work question goes? No. Could it be an issue on an exam? Yes. The exam is multiple choice. How is it going to manifest on the exam? How do you know you need to be concerned about stereochemistry on the exam?
It'll tell you.
Sort of. There's wedges or dashes where? Look at your answer choices. Do the answer choices show wedges and dashes? Damn, I got to watch out a little bit more carefully for this. Right? Is this one to show that? Probably not. What hints do you have? SmartWork didn't ask for it. Why did they not ask for it? Because of the whole carbocation thing, they decided it just wasn't relevant. Okay? So sometimes it gets asked, sometimes it doesn't, and a lot of that just depends on the scenario that you're looking at. You just have to be always aware that it's there, not necessarily always using it. Did I flog that question to death? Okay. No? You got what other questions?
It was wet. Lost
Lost where?
in the sauce.
Stop
good.
drinking.
I'm tired.
Next question. I don't blame you. Do we have another question? It's going okay. I like talking about chemistry.
Love it. If nobody else does, now, it's something, I'm gonna go over radicals, but I still don't understand that. You just know that it's one electron, that's it.
Okay. Radicals can be a pain. I intentionally leave radicals out for the most part, and you get a whirlwind lecture at the end on it, largely because I need to cover it, and there are questions based off of radicals. But it usually falls in a very niche category of chemistry, and it breaks the pattern of all the other chemistry we've talked about. Okay? If we think back to the arrows that we used in the previous reaction, what arrows did we use? Double, because what?
2 electrons.
You move 2 electrons. Radicals don't have 2 electrons to move. Okay? Which means if I'm going to react a radical, I'm reacting one at a time. Okay? Those were horrendously sloppy, so I'm going to have to fix that. Okay, single-headed arrows, it's better. It doesn't get much better than that. Okay, single-headed arrows to represent those single electron pushes. Okay, these are not an easy thing to navigate and draw. Okay, if we consider this reaction, where's that first arrow going? We're gonna have to, can I flip the script? I'm gonna have to flip the script. So I was gonna run a chemical reaction here. That's what I run, right?
Yeah.
How does my purple arrow look different than my red arrow?
2 heads.
2 heads, keep going. What did you say? Charge to charge. You had to make an observation that was true, but then invalidated my process. No charge. What's that? Okay. Whereas the first case is still moving electrons. Again, what is different about those arrows?
Or their shape.
Fish head versus not. If you're talking about the curvature of my arrows, knock it off.
Partial charge, 4 electrons. Attacking.
This is really, really subtle within the process, and it's not obvious to see. Okay? In the bottom one, where are those electrons going? They're going from the oxygen atom to where? The carbon. Where are the electrons going for the top carbon? If I wanted them to go to the bromine, you might have seen an arrow like that, where it gets closer to the bromine. It's not going to the bromine. Where is it going? It's going to empty space. Okay? We can emphasize it a little bit. It's going to the space between the carbon and the bromine. Well, what happens if I put an electron in the space between atoms?
They connect.
Nothing happens. What happens if I take another electron and put it in that same space? Now I've got a chemical bond. Okay? If you go into the smart work homework for this, which is technically extra credit, you will find there's not a lot of arrow pushing reactions for these. Okay? And that's because you're taking an arrow and putting it into empty space. How does that get graded? Not well, is ultimately how it gets graded. Okay? And so they usually end up forcing some kind of, we're trying to make a connection between the carbon and the bromine, so we're going to put the electrons into that connection space. Okay? It's pretty backwards, and I don't like it. Okay? But there's not a better way to grade it. Okay? We encounter another issue here. Okay? Where did our lower arrow go from? Went from the bond, right?
Yeah,
Well, how many electrons are in that bond?
2.
2. I just took 1 out. What happened to the other electron?
It goes with one of the other.
Okay? At this point, it's sitting in the bond, but I now don't have a bond, so I have to specify where that last electron went. That last electron has to go to the other bromine. Okay? So in our radical reactions, you see arrows explode in number because we have to explain where every single electron goes, and that's obnoxious. Okay? But that's part of that process. Right? So there's one big major difference. Okay? You're changing how electrons, or how we represent how electrons are moving. Okay? And all of it is a human representation, and it doesn't fit nicely, so we have to create a new system. Okay? The next thing that comes about that becomes important is recognizing what kind of chemistry we expect. So when I draw that initial carbon radical, okay, what does it equate to as far as its reactivity? Okay, because I can say, well, now that I have it, I can do something with it, but am I allowed to have it yet? Said conversely, the carbocation, great, now that I have it, I can react it. But if I drew this for my carbocation, should I be discussing this reaction at all? No, why not?
The carbon, the central carbon there is the cation.
Mhm.
Just take from the hydrogen.
Nope. Why should I not even be having a discussion about the bottom reaction?
Why?
What's the most reactive thing?
Charge.
What charge?
Charge in the carbon.
Okay. Classify that carbon.
Carbocation.
That's its name. Classify it. Is it tertiary? For it to be tertiary, it needs to be connected to 3 carbons. Is it tertiary? Is zeroary. Do zeroary carbocations form? No. So what I'm drawing a picture of is what happens when I run into a unicorn. Okay? That's all and well for my imagination, but we aren't trying to do our imagination. We're trying to draw reality within the system. Not a useful thing to look at. So we can go back and say, oh, I can do curved arrows once I have a radical. But if the radical never exists, that's a dumb system to talk about. So when can a radical exist? When can a carbocation exist?
When there's carbons around it.
Okay. So we have to discuss something about what makes up a carbocation, what makes up a carboanion. And we looked at a carbocation. Carbocations are unstable because why? They don't have electrons. So what do we do to say that a carbocation is allowed to exist?
Around it.
There's more electrons around it. We get secondary carbons. We get tertiary carbons. We get resonance. If we think about the anions, the negatively charged carbons, when am I allowed to have a negatively charged carbon? What makes a negatively charged carbon reactive? What's that? True. Keep pushing on it.
You mean true. So there's no electrons around it, just hydrogens. So
No, there are electrons. That's why it's negatively charged.
not as much as if it were carbons.
Ah, so if we're looking at the anion stability, it's reactive because it has too many electrons. So for it to form, it needs to form in a system that has less electrons around it. Zeroaries are now okay. tertiaries are now bad. Does that make sense? So what you have done is pushed to their natural chemical reactivities. Positive charges are missing electrons, so give them electrons. Negative charges have too many electrons, so don't put electrons around it. So now go to the radical. What makes the radical unstable? And this becomes the hard question. Is it unstable because it doesn't have a pair of electrons and therefore needs more electrons? Or is it unstable because it has a single electron and it wants to give it up? I get both of those potential answer choices, which changes the reactivity drastically and my interpretation thereof. It means I can evaluate the radical as an anion. I want to get rid of electrons. Or as a carbocation, I want to accept electrons. That's very problematic. Okay? So how would we decide which reactivity was the primary reactivity?
Maybe we'll see what it's reacting with. Maybe see the electronegativity.
Test it. I just go in the lab and I test it and say, how does this react? When does it form? Right? And what we discover is that radicals approximate carbocations. Really, I should just say cations. Which means if I'm talking about a chemical reaction where I want to form a radical, where would I prefer that radical to appear?
A more stable carbocation.
Wherever I would have a more stable carbocation. So if I look at this scenario and I would say, bam, I'm going to do something crazy. Okay, wildness. Okay, wildness happens and I form a radical. Where do I want to see that radical be?
In the middle of the tertiary.
There's my radical. Okay. That's pretty much it. Okay. So radical chemistry, think about them like carbocations. That predicts out the chemistry. Okay. Radical chemistry, you have lots of curved arrows. Okay. And all of those curved arrows are single curved arrows, single hook. Okay. We're going to push on it a little bit further here. What changed to go from this structure to this structure?
We had one single electron.
If I added an electron to that carbon, what happened to it? How many electrons would it have around it? Answer my question first.
So did it break octet?
It would break its octet. If I add an electron to that carbon, it started with 8, and I add an extra electron, it has 9. I've exceeded the octet. Can I do that? No. So did I add an electron?
No.
No. What did I do?
Took away the hydrogen.
Ah, there it is. There's an implied hydrogen there. And somehow or another, what I did was I took that bond of 2 electrons, one went with the carbon, the other one went with the hydrogen. Right? Is a hydrogen radical particularly stable? No, so we would need something to pick it up. Okay? Typically what we throw in there to pick it up, we'll come back to where this comes from here in a second, is something like bromide. Bromide donates its 1 electron in. Why does it donate it to the hydrogen and not the carbon? Where are those atoms located? True, tertiary. Where are the hydrogens relative to the carbons? On the outside. If we're looking at radicals, radicals are wicked reactive chemistries. What are they going to react with? Whatever's closest, which means the outside. There's our hydrogens. Right? Where did that bromine radical come from? You're right, I had to have made it somehow. We're talking about a bromine with just a single electron chilling on it. What could I bond bromine to that it would allow one other electron to be given up? Say again? Okay, that bond is 2 electrons shared between 2 bromines. Where are those 2 electrons preferenced? Neither spot. Okay? But Mike, with alkenes, we reacted bromine and bromine reacted as a positive. Right? With alkenes. Alkenes provided the electron source to polarize the bond. That's what caused it to break. If I got just bromine chilling on its own, what's polarizing the bond? Exactly, nothing. Nothing's polarizing it. Okay? So how do I make the bond break? Because there's energy in the bond. Well, how do you make any bond break? Or go all the way back to exam 1, our short answer on exam 1. There was a question about double bonds, and everybody was like, I don't know how to answer this question. Like, this is stupid. Why would we ever do this kind of thing? It's not resonance. What? Yeah, how do we transition between cis and trans? Because that's a double bond. I can't rotate a double bond. Rotation of the sigma bond. But I've got a double bond. What do I have to do the double bond?
Make the electrons jump to a higher.
And I can make electrons jump from one orbital to the next using light. So when we're talking about how we get radicals, we need a source of energy. Okay? It can be in the form of heat, but that heat has to match the energy of that bond. So they get tied very specifically to certain reagents. So we got to be kind of careful with that. So light is what's used to break that bond. Light comes in, excites the electron. The electrons go back to their individual partners, and we get 2 of those bromine radicals. That bromine radical is now swimming around, and it happens to bump into our alkane, okay, which we're going to come back to in a little bit. It sees the hydrogens, pulls a hydrogen off to stabilize. We now have HBr. Instead of having bromine radicals floating around, I have H plus and Br minus. Br minus is relatively stable. I'm now in an acidic environment. Right? So cool, I've got this radical floating around. Now what do I want to do to it? React it. Right? What could I potentially put near that bromine radical?
So there's Br plus.
There's no Br plus, there's Br minus. The problem with Br minus is Br minus brings in 2 electrons and I only need 1. So I could, big old air quotes, pull the other bromine radical that I formed and bring that in. Okay? So which is now going to shift us to kind of the next topic within radicals. What happened in the very first step? Okay? I broke stable bromine into a bromine radical. What happened in the next step? I started with a radical and ended with a radical. What happened in the last step?
Radical
2 radicals, and I ended
molecule.
with neutral molecule, no radicals. Okay? You might have just started mouthing that. Okay? The whole thing that's necessary to cause this reaction to work is the presence of radicals. So we might call special attention to the formation of those radicals. We might call that an initiation. Okay? Where the radicals have all disappeared. Radical killed radical and we're now neutral, we might call that termination or endination. We use termination. Okay? What's happening in the middle state? We have a radical that also formed another radical so the reaction can continue. I may have lost a radical but gained a radical. That's just going to continue. That's now a propagation. Each of those three stages have varying ways that they can be formed. Okay? But typically in kind of pseudo-rare-ish circumstances. For instance, the initiation only happens when light hits our elemental bromine perfectly to cause that excitation, to cause the bond to break, so that the bromine radical forms. But then what's the next piece of information? What if the bromine radicals that have formed have very low energy? How far do those atoms move if they have no energy? Not very far. They're very reactive, so what's that bromine radical likely encounter?
More bromines.
The other bromine radical. So our initiation very quickly can end in a termination. And we get nothing. So generally speaking, we need to ensure that we've got active motion of our particles so we can stir things around. We might even add a little bit of heat so our particles move more. When our light impacts, it's going to form that bromine radical in very low concentrations. The hope is that that bromine radical eventually, at some point in time, encounters the alkane. Because it encounters the alkane, we can now get a propagation, which now forms the alkyl radical. What is that alkyl radical most likely to encounter? And be careful. I said what's most likely to encounter. How many bromine radicals are floating around? Very little, which means is the radical likely to encounter another bromine radical? Nope. What's it more likely to encounter? Elemental bromine. So instead of being a propagation where our radical encounters another radical, we're more likely to see this scenario, where this is no longer a termination, but now a propagation. Because I still have bromine radical floating around. What's the most likely thing for that bromine radical to encounter? Bromine! So it does another propagation system where it cancels a bromine and reforms the radical. Okay? That radical is then going to continuously kind of hop around the system, encountering whatever it most likely encounters. That most likely encounter is heavily dependent on concentration. And yet none of our reactions specify concentration. It is all implied within the reagents, which means you have to be familiar with those reagents and what those implications are as far as concentration goes. Okay? Could this alkane radical hit another alkane radical?
Yes.
Yeah, which means the structure could get bigger. Okay? And what it could end up forming is a fun little system known as polymers. So if you've heard anything about polymer chemistry, this is one of those systems. Okay? And you can now get chain growth, and you can get polymer chemistry continuing out of this, which is neat. Okay? Those are controlled based solely off of concentration. Okay? So subtle changes in concentration make a huge output within this. So we talk about radicals, lots of single-headed arrows, okay, are radicals. Talk about radicals, they're roughly carbocations. Try and make the most stable carbocation you can. Right? And we'll talk about an exception to that. You need to be familiar with identifying initiation, propagation, and termination steps, right? Which we walked through. Initiation, I have no radicals, I end radicals. Propagation, start radical, end radical. Termination, start radical, end no radical. Remember, the termination step on the board currently is no longer correct because we turned it into a propagation. Kind of make sense? The last specific piece, which we've already started trying to allude to, is now very specifically the reagents involved. So when we talk about radicals, you're supposed to know the reagents. that's this slide. Right? And if we consider, actually I'm going to escape that, if that's what I'm saying is our radicals, if we consider that when we looked at addition reactions, it was this slide, and this slide, and this slide, the radicals, relatively thin and slim. Okay? So there's less radical stuff to go through and memorize. So for me, my recommendation is just memorize the radicals and hope for the best. Okay? And then I would spend the rest of my time learning the other content, because the radicals break from that content and add a whole nother layer of crap that you have to deal with that doesn't match anything. Hence memorization. Kind of, sort of? Right? Note, again, there's nothing about concentration specified in each of these reactions. Okay? A couple of things I'm going to point out. Right over here, this is not radical. Why is this one shown? Because this is trying to address this bromine in the alkenes. We got to be careful because we can do just a normal electrophile addition. How do I know I don't want to do an electrophile addition? What's different when I react Br2? I didn't show it. Oh, jerk. Too messy. It's as neat as you get, for the record. How do I know I want Br2 acting as a radical with an alkene and not electrophile addition?
Well, addition of light.
You mean an extra source of energy that causes the radical to form? Yeah, that's why it's important to identify that extra source of energy. Okay? And if we go through and look, light, 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 heat. Why is that one all of a sudden different? The thing that makes the radical roar, okay, is a different bond. It's not Br-Br, it's oxygen-oxygen, okay, which interestingly enough requires a little bit more energy, okay, because we're moving to heat from visible light, okay, and that's what causes that oxygen-oxygen bond to split, which then gives us our radical that can then make that cascade of reactions.
So we just memorize ABR, light, heat, HBR.
So what you're trying to memorize is what's happening in each of those scenarios, okay? NBS, I think, would go right back nice and easily to what T-but, what's NBS? You don't want to know what NBS is. You really don't. NBS is a reagent when mixed with light and an alkene puts your bromines. Okay? That's all you need. If you know that, you're fine. Okay? Kind of, sort of? Yeah, and it may sound, oh, it's actually to memorize. You're not looking at tons of questions on radicals. Okay? I'm not the only one that thinks they're a relatively minor, major part of organic chemistry. Okay? If we consider all of the chemicals we've used, almost every single one of them has gone through a radical reaction to get to you. Okay? Why? Where do all of our chemicals come from? It's a fun little dirty secret about chemistry, at least organic chemistry. Dead dinosaurs. It's all petroleum based. Okay? So we pump oil. This is why I'm kind of anti like gasoline cars. You take, I mean, there's lots of reasons to be anti them. But in any case, you're taking petroleum, okay, carbons and hydrogens, you're taking it out of the earth. Okay? It is the fundamental basis for probably 90% of this room. General composition. Whiteboards, you're coming from petroleum chemistry. The tabletops is petroleum chemistry. Okay? And what are we doing with that petroleum? We're burning it so that our cars move. So we're taking the fundamental building block of our natural existence and we just torch it. It's like, I'm hungry, so I'm going to go home, I'm going to take my bread out, and instead of, making a sandwich, I'm just going to burn it. Because, what the hell? Okay, and I'm not talking toast for the record. Okay, that's what we're doing. It's a bit silly. Okay, so that's our radical system, our big overarching summary for all those individual pieces. Okay, if we take a look, we said bromine, our radicals form the most stable carbocation. There's our substitution, right? What happened with chlorine?
Mixed products.
Everything. We got a mix of products. Why? It's kind of that chlorine's weird. When we run these reactions, we're almost always referencing our halogens. Bromine is the only one that I generally care about, which is why when I talk about radicals, I say form your most stable radical, or your most stable carbocation, because that drives the chemistry. Why do I not talk about forming a primary radical? Well, because it's unstable, and the place that I form it means that I get a mixture of products. As organic chemists, our goal is to make something. Not to make something and a crap ton of waste that I don't want. Chlorine is not selective. Okay? So if we mix chlorine with light and an alkane, anybody's guess, we get tons of different products. If I mix it with bromine, I get very predictable products. That predictability is a good thing. Okay? What happens if I use iodine? Put it this way, chlorine is unpredictable, bromine's predictable. Iodine? Predictable. Very predictable. So predictable, in fact, that if I try to run the iodine reaction, it takes years. Okay? Very long reaction times. What about fluorine? Yeah, it's very unpredictable. It's so unpredictable that it predictably explodes when you mix it with alkanes. The reaction is so fast, it just give me hydrogens immediately, and immediately explodes. That's very problematic. We don't like that. Okay? So the only two reagents that you ever really see with radicals are chlorine and bromine, and chlorine's really only added in there to just mess with your head. It's not quite that bad, but it's pretty close. Okay? Why else do we care about radicals? Just to bring it back to reality a little bit. Summertime, right? What some of us put on our skin during the summertime? Sunscreen. Why do you put sunscreen on?
UV light.
Why do we care about UV light?
Cause burning.
What is the UV light doing?
Burning.
Making radicals. Okay? Why is it causing your skin to blister? It made radicals, which did what to your cells? Exploded them. Yeah, that's kind of problematic. Okay, and not quite exploded. What it ended up doing was causing the cells to do cell death. They're like, oh, I'm mutated. This is bad. Die. Okay, that's how our system works. It's a neat system. Okay, and when it fails, what happens?
Cancer.
You get cancer instead. Mutated cell goes, hey, cool, I'm mutated. This is fun. Let's just grow. No, that's not how skin works. Okay, and you get skin cancer. Okay. So radicals are something that we protect ourselves against when we talk about sunlight. Cellular respiration, oxygen. Okay? Oxygen does radicals. Particularly when I have an O-O bond. We always talk about, the danger of, you're all medical people, you not heard about danger of free radicals? Okay? Never heard of free radicals. You'll hear about it in dentistry too. They use it with dental polymers. Okay? Free radicals are dangerous. Oh, we don't want free radicals. That's how we respire, like breathe. Get energy to move around our body is through single electrons, through radical reactions. Okay? So it's not the radicals that we don't want in our body. It's the
Unwanted radicals.
the free radicals that are just like, hey, what's going on? Oh, I'm going to take that bond. Oh, sorry, I just killed you. Okay? Okay? Free radicals are a problem. Radicals are things that we actively want through our systems. Okay? That's how electron transport chain, those kind of things function, is through electron transfers. Okay? So it is a really neat area, but makes up a really tiny portion of what we end up dealing with.
Is it like
how can you say it acts like a nucleophile? It donates an electron, a single electron, and nucleophiles donate 2 electrons.
So,
Not only does it donate a single electron, it accepts a single electron. So you can't really label anything within radicals as nucleophile and electrophile because they don't fit the definition. It's a radical reaction. That's why, again, I segregated it to the very end of the semester because it's separate from all of the content we've already addressed. Okay. Last piece that I'll point out, if we look at the overarching chemistry behind this that we really care about, okay, with our alkanes, what kind of reaction are we doing? What did we do? Don't tell me radical. I know that. Substitution. What'd you substitute? Hydrogen for bromine. If we look at our alkenes, okay, our alkene reactions, let's look at this one. What kind of reaction do we do?
Addition? No.
Not addition, we still have the pi bond. Substitution. What do we substitute? Hydrogen for bromine. Okay? Why do we care about substituting hydrogen for bromine? What was that hydrogen connected to? What kind of bond is a hydrogen to carbon bond? Nonpolar covalent. Do those bonds react? No. It might mean that if you're trying to react a nonpolar covalent bond, you might need to do something a little bit radical. Okay? And that's what's going on with those. So if you're looking at a starting structure, you're like, I don't see any reactivity, it's probably a radical. Okay? The last one is technically doing an addition on here, but this addition is interesting. Why is this addition interesting?
You eliminated a pi of the sigma.
That's addition, yeah. Predict the product.
take the alkene, create the carbocation, connects to the hydrogen, bromine goes.
Where's the carbocation?
On the left-hand side. So, yeah, right there. It creates a hydrogen. And then bromine comes in negatively, attacks.
And yeah, that's a good response. So we did addition, right? We added H and Br across the pi bond. Everybody happy with that? Like take that mental picture. What happened?
There's only one
Radical.
sigma bond.
What's that?
There's only one sigma bond.
Careful. What changed? Okay, so there's 2 observations. The bromine reacted differently. Our bromine's at a different spot. To there only being 1 sigma bond. There is another sigma bond. It's there to our hydrogen. Okay, so the hydrogen is implied. Where did the H in the bromine go? Opposite the way we would expect. Why? In radicals. Kind of makes sense? Actually, it doesn't have to make sense. That's just what it does. Just accept it.
Something weird.
Okay? So if you're looking at an alkene where they're going on backwards, make it radical. How do you know it's radical? What? How do we know it's a radical reaction? What should you be looking for when you're doing an addition reaction that added H and Br? They went to the opposite location. Roar. Why does everybody think that's funny? That's what it says. Roar. Is that better? It's too much of an A and roar. 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 Do we have a different question? It's definitely on a recording. Not quite as bad as the Bulls lecture. Next question. You won't be able to find it. Don't worry about the other one. No other questions? I mean, I can schedule Thursday's room to be twice as the time and just take the final in. No? Okay, I was just checking. So you still have questions then?
I feel like we need to go over my personal material first. I'm still trying to get through that. Huh? So it could be additional, yeah, maybe additional.
Ooh, I like this question. We're going to do this question. It's not that bad for people being like, oh.
The additions?
No, it's not an addition. Though I do kind of question, oh no, it is in that chapter. Oh, look who's coming through the door. Somebody got what I was trying to do. Maybe it made sense. As long as one person gets it. If you don't get it, that's okay. Don't worry about it. I'm used to it. How do we figure it out?
If I could like react to it, going into this,
This is part of the reason why I like this question.
You can see the faded circle.
What's that?
You can see the faded circle.
Just because it's a faded circle doesn't mean they're right.
but I'm gonna pick it anyway, it's electromagnetic.
Why do I care about electronegativity?
Could it pull the electron more towards it?
Why does that matter? Where does it say anything about acidity?
It's reacting with NaH. Is that an acid or base? Remember?
Yes.
Yes.
Okay. So, and this is something that I've been trying to teach you to do. Don't focus on memorizing reagents, focus on the chemistry. Oh, I don't remember. I don't give two flying rats' butts what you think about what you think you memorized. The problem with memorizing is that will only work for maybe the first 60 minutes. You still have 50 more minutes of testing to get through. You're going to be brain dead. You need to rely on something other than rote memorization. What do you see when you see NaH?
Positive sodium and negative hydrogen.
Why is the sodium positive?
I just,
It's a metal and a nonmetal. What do we know about the sodium?
it goes away.
Goes away, which then means
Hydrogen.
you're looking at hydride. What is the reactivity of hydride? Fair. Try again.
A lot.
What makes hydride reactive? What charge? Negative. What makes hydride reactive?
Negative charge. It's electrons.
Thank you. Okay? It has electrons. Hydride is an electron donor. What do we want to donate those electrons to?
Positive.
True. Positive. Okay? And I'm still not even looking at the answer choices yet. What about the question, what positive should I be looking for? Why hydrogen? Because it says in the question, which hydrogen atom is most likely to be... What the frick is abstract? I don't care what abstract it is. I know hydride is H-, which means the hydrogen I'm reacting with should be... And if I'm now trying to identify an H+, what should I be looking for?
What's the set of hydrogen?
What ranks acidity? You freaking said the answer earlier. Jeez. No, you weren't wrong.
Oh, okay, that's going to.
We look at the atom where the hydrogen's connected. We compare oxygen, carbon, carbon, carbon. They all have the same charge. Do they have the same size? Yes, because they're in the same row. Do they have different electronegativities? Carbon does. What does that mean? Sorry. Well, technically that's true, but I meant oxygen. Oxygen is more electronegative than the carbon. What does that mean?
It's going to pull the electron from the bottom closer to itself,
Making that hydrogen
acidic.
more positive and more acidic. There's my answer. Okay? So whether everybody processed through that or not, I don't know. Okay? But what Abby went through was acidic. None of that content knowledge was being stated right away. Okay? And she might have said that because she's done practice with it. Or maybe she saw that it came, all the stuff I erased had reference to acids and bases. Okay? You don't get those extra hints. So try to use the context of the question to outline what you're looking for. And if we process through it, the what you're looking for is exactly what I've told you to do for every single question we've ever solved. Okay? Push to those patterns, make those intentional choices, use the information you have to predict where you need to go. With that, we're done.